hope you had a look at the night sky last night and you could identify Orion and Ursa Major and also get a feel for the things that we talked about in the last class, particularly RA and dec, right ascension and declination. In the last class, we saw that the motion of the sun and the planets and the moon on the sky can be interpreted in terms of the moon going around the earth and all the planets going around the sun. Now, the study of these orbits, the motion of these planets and the moon is what led to the birth of what we now know as mechanics. So, the mechanics that we learn in school, high school and in college can essentially be traced back to the study of the orbits of planets and the moon around the earth, trying to understand that. And one can explain, one can mathematically quantify this whole thing using the Newton's laws of motion. So, the Newton's laws of motion, you may say, came about from the study of these orbits, okay, trying to understand these orbits. So, there are two things that are required: Newton's laws of motion, which we all know, so that is the first input, and the second thing that is required is the Newton's universal law of gravity, the universal law of gravity. Both of these were proposed by Newton. And the second one is a very remarkable thing. It tells us that any two objects in the universe exert a force F which is equal to, so if there are two objects, this object will experience a force due to the gravitational interaction between these two objects, and the force is going to be directed, it is an attractive force, and it is going to be minus g m m by r square, where m and m are the masses of these two objects. And such a force acts between any two objects in the universe. And it was a great realization, it was a great jump, the realization that the force that pulls an apple that falls from the tree down to the earth, the force that holds us to the earth's surface, is also the same force that is responsible for the moon going around the earth and the earth going around the sun. So, this is a universal, it is a universal law. It is not specific to a certain place or object, it is universal in nature, it holds for any objects, any object. Okay, so, using these two, one can explain these orbits, one can quantify these orbits. Before we go further, let me also briefly discuss another point. We now know that there are four fundamental interactions in nature. We have the strong interaction, the weak interaction. So, we have two nuclear interactions, one is the strong interaction, strong nuclear interaction, and then we have the weak nuclear interaction, and we have electromagnetism, and we have gravitation. Now, the first two interactions are short range and in astronomy we are usually dealing with the motion of very objects at large distances from one another. So, these two are not very relevant if you want to study the orbits of say planets or on larger scales, motions on larger scales. So, there are only two possibilities, that the forces there could be electromagnetic in nature or they could be gravitational in nature. We also know that the universe on the average, if you take parts of the different objects in the universe, they are on the average neutral, they do not have any excess charge. There are limits one can place on this, and the electromagnetic interaction acts only between charged particles. So, this again is not a very important force if you are trying to explain the orbit of planets around the sun or the moon around the earth or various other motions that we observe in astronomy, in the universe, on large scales in the universe. So, it is gravitation alone which is important. Okay. So, much of the cosmology, much of the dynamics which is relevant on astronomical, so for astrophysics or for cosmology is gravitational dynamics. These other three also play important roles, but if you want to study large scale motions, they are governed by gravitation. So, this is an important point to bear in mind, and we shall now study the motion of objects under the influence of the gravitational interaction. So, we are going to start off by writing down the Lagrangian, and the system that we are considering is as follows. There are two objects. So, what we shall study is called the two body problem. So, there are two objects of different masses m1 and m2, and we choose some origin for the coordinate system, and r1 r2 are respectively the vectors, the displacements with respect to this origin. So, they are the displacement corresponding to these two positions. So, they are the positions of these two particles m1 and m2 with respect to some arbitrarily chosen origin. Now, the interaction between these two particles, it depends only on the Newton's laws tell us that it depends on the mass of this object, it depends on the mass of this object, and it also depends on the distance. So, it is a function of only the distance between these two. Okay. So, we can write down the Lagrangian for this. Now, those of you who are not familiar with the Lagrangian, there is no reason to worry. We could have equally well proceeded by writing down the Newton's equations of motion, okay. But this is an easier approach if you know the Lagrangian formalism, which I presume many of the students here know, then it is an easier approach. Okay. So, we shall adopt the Lagrangian approach, but you can arrive at the same result from just the Newton's laws of motion. So, let us write down the Lagrangian for this. So, the Lagrangian L will have one term corresponding to the kinetic energy of the first particle. So, that is going to be m by 2 r1 dot square. This is the vector velocity squared, basically the velocity of this particle squared. It is the kinetic energy of this particle, and then we have the kinetic energy of the second particle plus m2 by 2 r2 square and we have to subtract out the minus the potential, interaction potential between these two particles. And here we shall do a very general analysis to start with. So, minus we will write that there is some potential which is given by u, and u is a function of just the distance between these two particles. So, u is a function of mod r1 minus r2. So, r1 minus r2 is the separation between these two particles. The potential, the interaction depends only on the distance. So, gravitational potential we know depends only on the distance between the objects. So, here there is some potential, some interaction potential which depends only on the distance between the objects. So, this is the two body problem, and we would like to analyze this problem. We would like to solve this the motion of these two particles. Okay. So, there are 6 degrees of freedom, 3 for this particle and 3 for this particle, and there are the 6 corresponding momenta for these 6 degrees of freedom. So, the degrees of freedom are the 6 different coordinates. Now, it is the problem is, if you write down the equations of motion, you will get 6 equations of motion which will be coupled. The problem is considerably simplified if you shift to a different coordinate system, and the different coordinate system that makes the problem easier is as follows. One coordinate r, let me write down the coordinates. So, there is one coordinate r which is the center of mass of the system, and you can calculate the center of mass. It is not very difficult. The center of mass is m1 r1, the weighted sum of the distances r2 by capital M, where capital M is the total mass of the system. So, we are changing coordinates. We are, instead of choosing the positions of the individual particles, it is equivalent if you specify the center of mass and if you specify the relative displacement between these particles. So, we shall use r to denote that, and r is r2 minus r1. So, it is, we shall use these coordinates instead of the coordinates of the individual particles. These coordinates are convenient because the potential, the interaction depends only on the separation between these two particles. So, now we use the displacement between these two particles as a coordinate. So, this also has 6 degrees of freedom. So, you can equally well describe this system using these two vectors instead of r1 and r2. Okay, so, we have to just transform everything from these coordinates to these coordinates. So, to do that, let us just do the algebra. It is not quite straightforward business. So, let us go through the algebra, a little bit of algebra. So, we have m into r. So, we are just writing this equation again. So, m into r is equal to m1 r1 plus m2 r2. And we also know that the displacement, the separation between these two r is r2 minus r1. So, I can write r2 here and minus r1 here. Now, what we will do is we will multiply this with, so we want to, let us say, first eliminate M1. So, we will multiply this with M1. We want to eliminate R1. So, we will multiply this with M1 and add these two equations. So, if you do that, what we get is this cancels out, and what you have is M R2 is equal to M R plus M1 R, or R2 is equal to R plus M1 by M into R. Okay, so we have worked out what R2 is. Now, we have to just repeat the same exercise using eliminating R2 from this. We have now eliminated R1. So, to eliminate R2, let me just write down the equation here. So, if you want to eliminate R2, what you have to do is you have to multiply this equation with M2 instead of M1. So, what we have to do is M2 R is equal to M2 R1, and we will minus this will have a minus sign. So, M2 R2, and we will multiply this whole thing with a minus sign, so that this cancels out. So, we will have a minus sign here, this will have a plus sign, this will have a minus sign. Okay. So, we have these two equations, and when we add these two equations proceeding in exactly the same way, what we get is M R minus M2 R is equal to, this term will now cancel out. So, we have M R1, or what we see is that R1 is equal to R minus M2 by M R. I hope this is okay, right? Right. So, that is what we get. So, we have these two expressions for R1 and R2 in terms of capital R, which is the position of the center of the mass, and R, which is the displacement between the two particles. Okay. So, what we have to do next is we have to substitute this in the expression for the Lagrangian. So, let us do that. So, the expression for the Lagrangian is shown over here. Okay. So, we have to substitute these expressions for R1 dot and R2 dot, R1 dot and R2 dot. So, a dot will just time derivative of this and this, time derivative of this and this, the square of that we have to substitute here. Okay. So, we have to substitute these two expressions here. Now, let us just do this exercise quickly. So, when I square this and multiply it with M1, I will have also another term, the square of this multiplied with M2. So, when I add these two terms, so I am going to square this essentially, I am going to square this and I am going to square this. So, there will be one term which is, let me write down the resulting Lagrangian. The resulting Lagrangian is L there will be one term which is half L half m r square, that comes from the square of this and the square of the derivative of this when I put them here. Okay. Then there will be one term which is the product of this term and the product of this term. Now note that there is a m1 here for R2 and R2 is multiplied by m2. Similarly, there is m1 in R1 and that is multiplied m2 for R1 and it is multiplied by m1. So, the cross terms, when I square the derivative, time derivative of this, the cross terms will essentially cancel out, and the term, the square of this plus the square of this is going to give rise to another term. So, let me write that. So, what we have is one more term which is plus, so we have m2 m1 square by capital M plus m1 m2 square by capital M, this into r square by 2, and we have minus u which is just a function of r. Okay. And here we can take m1 into m2 common outside, there will be m1 m square here, sorry, the denominator, right. So, one term comes from the square of this, one term comes from the square of this. And here I can take m1 m2 common. If I take m1 m2 common, what remains is m1 plus m2, which cancels out with one of the m's over here. So, what we get finally is that we can write this as half m r dot square plus half m r dot square minus u r, where this m is called the effective mass. And it is 1 by m is equal to 1 by m1 plus 1 by m2. Okay. So, we have gone through the algebra, and what we see is that in terms of these new coordinates, the two body problem can be written as just a free particle motion of the center of mass. It turns out that you have just a free particle motion of the center of mass here, and you have this motion of the displacement between the two particles, which is governed by this Lagrangian, where the mass that now comes in is the effective, is not the effective, it is called the reduced mass, sorry. It is called the reduced mass. Okay. And the reduced mass is 1 by m, is m, which is defined such that 1 by m is equal to 1 by m1 plus 1 by m2. Okay, you just do the algebra, you can, if you just simplify this, you will find that this is the mass that you get over here. Okay. And the center of motion, the motion of a free particle is not very interesting. If it is at rest, it will remain at rest. If it moves, it will continue to move with the same uniform velocity. So, that is not of much interest. So, we can drop this term, and the entire two body problem now reduces to a one body problem. The one body problem is that there is a particle of mass m at a distance r. Okay. So, there is a particle m, and this particle m is under the influence of a force which acts towards the origin, where the origin now, right, the potential depends only on r, and the force is the gradient of this potential. We know that if the force on this particle is minus gradient of u, and since this is a spherically symmetric function, a radial function, the force which is the gradient of this u minus gradient of this u is going to be radial. It is a radial force. This is called, so the whole thing is a centrally, it is a central force. So, this is called the central force problem. The force acts towards this center. Okay, this is called the central force problem. So, a two body problem where they interact with some kind of a interaction which depends only on the separation can be reduced to a central force problem, where there is one particle which experiences a force which acts towards the center, either towards or away, and that force is represented by a potential which depends only on the distance r from the center. So, bear in mind the relation between the system that we started out with. The system that we started out with had two particles. Now, we have just one particle of mass m, which is the reduced mass of those two particles. The distance r, the displacement vector r, the position of that particle is essentially r2 minus r1. So, it is this vector, the displacement vector between these two particles, and this displacement vector r2 minus r1 is what we are now studying. Okay. And the center is now fixed, I cannot choose it arbitrarily, it is the center of mass of this, the origin is the center of mass. So, this single particle which has the reduced mass experiences a force towards the center of mass. Now, this again you can, at the end of the day, if you wish, you can convert back to the motion of these two particles. Okay. Now, this is the Lagrangian that we have to deal with. This is the central force Lagrangian, and we know, it is a well known fact that if you have a Lagrangian that is invariant under rotation, a Lagrangian that is spherically symmetric, invariant under rotation, then there is a corresponding conserved quantity. That conserved quantity is the energy. So, this, so we know is the angular momentum. So, we know that for this system there are conserved quantities So, one of them, there should be quantities. One of them is the angular momentum. And the angular momentum is conserved because the whole thing is spherically symmetric. The potential depends only on the distance from the center. It does not depend on the direction. The whole thing is rotationally invariant, and if you have a system that is isotropic or rotationally invariant, the angular momentum is conserved. Corresponding to there is this symmetry, there is a conserved quantity, the angular momentum. There is another conserved quantity for this system, and that is the energy. Why is the energy conserved? Well, the energy is conserved in this case or in any case because if the system does not have any explicit time dependence. So, if the interaction, whatever force I have, is independent of time, does not have any explicit time dependence, then I have a conserved quantity corresponding to that symmetry, and that is the energy. So, here we have two conserved quantities, angular momentum, it is a vector m. So, there are 3 components of this, and there is one energy 4. So, totally there are 4 conserved quantities. Okay. So, the 2 body problem, so 2 particles interacting with each other through an interaction which is dependent only on the distance, has been reduced to a 1 body problem, where that single body moves under the influence of an external force, and that external force is a central force. It is isotropic. Okay. And once we have an isotropic force, then which is time independent, there are these conserved quantities, the angular momentum and the energy. Now, the angular momentum we know is r, mass of the particle, into r cross v. So, if this is the center of mass, if this is r and if this is v, then the angular momentum is perpendicular to both of these. Right, and that is the cross product, and it is a conserved quantity, and since it is a conserved quantity, we know that the direction of the angular momentum has to remain fixed. So, r and v have to continue to lie in the same plane, right. From the conservation of angular momentum, we can say that the motion is going to be restricted in this plane, the plane defined by r and v at any instant of time, and the motion is going to be planar. So, this implies that the motion is planar. So, the conservation of angular momentum implies that the motion of this particle, which is the reduced mass of, which has the reduced mass, it is going to be a planar motion. Okay. So, the motion under a central force is always a planar motion. We now know this, and that is a consequence of the conservation of the angular momentum. Okay. So, we can choose a plane aligned with this plane of the motion, and in this plane we now have 2 coordinates. One of these, so this is the center of mass, one of these is r and the other coordinate is phi. 2 coordinates suffice in the plane to completely describe the position of the particle, and the Lagrangian can be written in terms of these 2 coordinates now, and the Lagrangian is m by 2. So, we have one term corresponding to the velocity r velocity, which is r dot square, then another term corresponding to the phi motion, which is r square phi dot square, and we have the potential u, which is a function of r. So, this is the Lagrangian that we have to deal with. Okay. So, this is considerable simplification. We had 6 degrees of freedom, then it got reduced to 3, and the center of mass moves like a free particle, and now we have got only 2. The conservation of angular momentum tells us that, the direction, the vector. Now, this Lagrangian, notice, does not have any explicit phi dependence. It does not appear anywhere in this. So, the equation of motion, if you do not have any particular coordinate, that is called a cyclic coordinate, and the momentum conjugate to that is conserved. So, if you write down the equation of motion, and del L del phi we know here is 0. So, it tells us that the momentum conjugate to phi is conserved, and let us calculate that. So, del L del phi dot, if you calculate that, it comes out to be m r square phi dot, right. So, what this tells us is that this is 0, or this quantity m r square phi dot is conserved, and this conserved quantity is very easy to interpret. It is the magnitude of the angular momentum, right. The direction of the angular momentum vector tells us we have a planar motion, and the equation for phi, it tells us that the magnitude of the angular momentum is conserved. So, this is m, the magnitude of the angular momentum. Now, this is a very important thing. Let me spend a little time just discussing this, the fact that the magnitude of the angular momentum is conserved. So, let us consider this is the center of mass and this is the trajectory of the particle, and let us say that this is the position of the particle at some time, and this is the position of the particle at some later time, and it has the angle between these two radial vectors has changed by an amount delta phi. So, let us ask the question, what is the area subtended by these two positions with respect to the center of mass, with respect to the origin, right. And this area, if the displacement is d phi, this area df, we can call it df, is equal to half times r times this displacement approximately, which is r d phi. Now, let us go back to the conservation of the angular momentum. We see that this can be written as m is equal to two into the mass of the particle into df dt. So, for any central force, the sectorial velocity, this is called the sectorial velocity, the sector covered per unit time, sectorial velocity is conserved. Okay. Or the orbit covers equal area per unit time, which is the Kepler's second law of Kepler observed these planetary orbits, and he proposed different laws for which phenomenological laws. So, one of these laws is just an outcome of the fact that we have a central motion, and the law is that in a unit time the orbit will cover equal area. In every unit time it will cover equal area. The area covered in some time interval is going to remain fixed. The sectorial velocity is a constant. So, this is called the sectorial velocity df dt, that is the area covered per unit time. That is a conserved quantity for any central force, need not be gravity. Okay, any force that is central, it acts towards a fixed center. Okay, so this is a very general feature of the central force problem. Now, we can use the conservation of angular momentum. So, this is the conservation of angular momentum. We have one more conservation law. So, let me write down that. The other conservation law is the conservation of energy. So, this tells us that E is equal to half m r dot square plus, now we have the, so this is the kinetic energy due to the radial motion, we have the tangential motion also, which is m by 2 r square phi dot square plus the potential energy u r, right, that is the energy that is conserved. So, this is the other conserved quantity, the energy of the particle. Now, what we can do is we can eliminate phi dot from the expression for the energy using this, the conserved of the magnitude of the angular momentum, the conserved magnitude of the angular momentum. So, phi dot is the angular momentum divided by the mass r square. Using this, we find that the energy is equal to a energy, this plus r square, we have a r square in the numerator, and when you square this, so when I square this, I will get r to the power 4 in the denominator, I will get m square, which will cancel out with 1 m over here, the half will remain and phi dot will be replaced by m. So, I have one term here which is m square by 2 m r square plus u of r. Okay. Or we can write the energy as m r dot square by 2. Now, notice that these two terms are just functions of r, and we can think of this as some kind of an effective potential, right. So, we can write this as plus u effective r, where u effective r is equal to m square by 2 m r square that is the effective potential. So, this whole thing has been reduced to a one dimensional problem where the energy is conserved and we have a new potential, the effective potential. Okay. This effective potential is the actual potential plus an extra term. Do you know what this extra term? Yeah, that is the centrifugal term. Okay. So, when you take the gradient of this will give you the external force, and this is the centrifugal force. The angular momentum is conserved, so you will have a centrifugal force. So, this term is what will give you the centrifugal force. Okay. So, this is a centrifugal potential, and it goes as 1 by r squared. So, the centrifugal force goes as 1 by r cube. Now, let us next restrict our attention to the gravitational interaction. So, we are now going to restrict our attention to the gravitational interaction. So, if for a gravitational interaction, let us now get down to business. So, we have for gravitational interaction the potential u r can be written as, what is the form of the potential for gravitational interaction? It is minus g m1 m2 by r, right. We know this, it is 1 by r, the force is 1 by r square, which we can write as minus alpha by r. Okay, alpha is this constant g m1 m2, and the effective potential is m square by 2 m r square minus alpha r. So, let us plot what the effective potential looks like as a function of r. This is very a very useful and instructive plot. So, let us make this plot. Now, as you at small r, r square is smaller than r. So, at small r it is the first term that is going to dominate. So, as r tends to 0, the potential blows up, tends to infinity. Okay. Now, there will be some point where these two terms are going to balance, and then beyond that it becomes negative, and as r goes to infinity, this will tend to, both the terms will tend to 0, but it is going to be, its behavior is going to be dominated by this term. So, the nature of this potential is going to be dominated by this term at small r, and it is going to be dominated by this term at large r, and there will be some transition region between these two. So, the graph looks like this, and here it falls off as 1 by r. So, there are a few general features that we have to note. First thing is, if the particle has a finite angular momentum, it will never reach the origin. Only particles with 0 angular momentum can reach the origin. If you have 0 angular momentum, this term is not there, I just have minus 1 by r, it is always negative, and the particle can reach the origin, reach the center of mass. Okay. Otherwise, there is no chance of reaching there. So, the motion is going to be restricted outside. The second point is that the energy is conserved, and it is equal to the kinetic energy plus this effective potential. So, if I have positive energy, it will never reach here. So, this part is out. The particle will come from infinity, it will reach a finite distance, and then it will turn back again. Okay. So, it will there will be a position of nearest approach, after which it will go past the particle. Okay. So, the trajectory for this energy, this is the center of mass, it is an attractive force. So, the particle will come, it will get attracted, and then it will go off like this. So, there will be a position of nearest approach, it never approaches never reaches the center. Whereas, for negative energies, E less than 0, we will have bound orbits. So, bound orbits will be there only for negative energies, and the orbit is going to be restricted between two values. The r1 and r2 is going to, the radius, the distance from the center of mass from the origin is going to vary between two values r1 and r2. So, there will be a point of nearest approach and a point where the particle is furthest. Okay. And you will have circular orbits. When do you have circular orbits? At the minima of the potential. So, at the minima of the potential, so there will be one value of energy for a given angular momentum, there will be one value of energy where these two curves will touch, that is the minima, and you will have circular orbits over there. Okay, and the circular orbits are stable in the sense that if you disturb it slightly, it will remain, it will just very close to the circular orbit, it will not diverge. Okay. So, these are the broad features of this problem. So, we are interested in bound orbits, closed orbits, no, bound orbits. So, the bound orbits are there for negative values of energy alone. Okay. So, we will have bound orbits for negative values of energy, and we have to solve this problem. Now, the procedure is quite straightforward. Let me very briefly go through this. So, how do you solve this problem? The way you proceed, you want to solve for the orbit. So, what you do is you take this, start from here, and this can be written in as follows. We can write it as m by 2 or okay, let me not proceed in this way, let me proceed as follows. So, here we have r as a function of time. Now, when we want to solve for the orbit, what we would like to get is r as a function of phi. How does r, we want to solve for the orbit, okay, how does r vary with time, with phi? Once you have r as a function of phi, it is very easy to eliminate phi and get it as a function of t using this. Okay. So, what we will do is we will eliminate time from this whole thing first. So, we will proceed as follows. So, we will eliminate time, and the other thing, simplification that we will do is we will use u, let us say x is equal to 1 by r as my variable. So, we will do two simplifications. First, we will use x, which is 1 by r, as my variable. So, let me do this. So, x dot is equal to minus right. So, this is x square, 1 by r is x square, 1 by r square is x square, and if I take it onto that side, I have r dot is x dot by x square, right. So, we can replace r dot in this expression with x 1 by r, that makes life a little convenient, that is all, okay, nothing profound in this, some algebraic steps. And the second thing is we will replace time derivatives with phi as my variable. So, from here, from this we get m r square d by dt is equal to m d by d phi. Okay, that is the conservation of angular momentum, right. D phi dt is equal to m r square d phi dt is equal to the angular momentum. So, we can write it in this way, and what it tells us is that d by dt is equal to, so I have m, then I have small m here, and I will have 1 by r square. 1 by r square can be written as x square. So, x square d by d phi. So, combining both of these, what we get is r dot is equal to m by small m, the angular momentum divided by the reduced mass, x square cancels out, dr d phi. Okay. So, what we have to do is we have to replace this r dot in terms of dr d phi in the expression for the energy, and then we have to integrate it. Okay, I will stop here for today, and we shall resume on this in the next class.